possible that they'll find things that you previously...
It's changed my thinking a lot. This notion, I wish I had time to really go into a proper discussion of the Higgs boson, because it's a remarkable cap of a 50-year intellectual journey. It's one of the greatest, next to perhaps Darwin's discovery of evolution, I guess is the way to put it. Next to that, I think in modern times, it's the most amazing intellectual journey humans have ever taken, and it should be celebrated as such. I really love talking about it because it weaves in all of modern science. I thought of writing a longer. I've written a bunch of short pieces about it. Maybe I'll write a long piece. But in any case, it really is this capstone of this journey that's involved theorists and experimentalists for 50 years, and it really is amazing. As a theoretical physicist, perhaps the most daunting thing in the world is to be sitting, from my case at night, because that's the only time I can seem to work, and to think for a moment that something you're working on is actually, that the universe actually obeys what you're talking about is very scary. And the good news is most of the time it doesn't. Most of the time you're wrong, so that's easy. But in this case, this notion that this beautiful edifice, the standard model of particle physics, fit together beautifully, but there was a missing piece. And the missing piece was that well, I'll give you. I can't help it. I'm a teacher. I'll give you a 2-minute discussion of it. I can't talk about how important it is without laying the groundwork. So the short version of this would be that there are these two forces of nature that are very, very different: the weak force and the electromagnetic force. And they're different as different can be. One's long range. One exists only over the size of the nucleus, and one is very strong. One is very weak. Neutrinos that experience just the weak force. There are 10,000 billion neutrinos going through every square centimeter of your body every second. And during the day, they're coming down from above. And at night, when you're sleeping, they're coming right up through the Earth. They don't interact. They go right up through the Earth, right through your bed, and right through your body. So think of that when you're trying to sleep tonight. And so the weak force is so weak that a neutrino on average can go through 10,000 light years of lead without interacting once. Okay, and so the electromagnetic force obviously isn't so weak it's responsible for us being able to see. But it was recognized that these two forces could be understood as different manifestations of the same thing, which is really surprising and unusual. But another very important characteristic of science, I forget where I first heard this described. I certainly know Richard Feynman did, but I think I heard it earlier. It might have been Jacob Bronowski. That one of the hallmarks of progress in science is seeing that things which on the surface seem very different are really different manifestations of the same thing. And of course, again, when I look at Richard, I think of evolution in that sense as well. One of the great beauties of Darwinian evolution is the realization that this incredible diversity of life can come from the simple beginning. It's really manifestations of the same basic biology. And so these two very different realms of the universe were recognized as saying, well, the mathematics can describe them as being the same, but there's a clear difference. Electromagnetism is long range, weak force is short range. Well, in physics, we understand that because the electromagnetism is mediated by particles called photons, the same things that we see. They have no mass, and that's the reason electromagnetism is long range, because the way the force works is I spontaneously create a photon here, and it heads all the way over there and gets absorbed. Now, if it had mass, when I created it here, it would take energy, and it would violate energy conservation. So quantum mechanics says, as I often say, quantum mechanics says it's like the White House or corporate America. If you can't see it, anything goes. And in quantum mechanics, so if I violate energy conservation, as long as I do it for a little while, so short a time that I can't see it, then it's fine. So if the particle disappears again, no problem. That's called the Heisenberg uncertainty principle. But so if it's a massless particle, it can take very little energy, and therefore it can last a very long time before you'd notice the violation of energy conservation, and that's why electromagnetism is long range. But the weak force is propagated by particles that are very heavy. And that's why it has a very short range, because when they get popped out, they have to disappear very quickly. So that was predicted and known in some sense. And but the problem is then, how could they be manifestations of the same thing? Well, maybe they're both massless. The particles that convey the weak force and electromagnetism are both massless at some fundamental level. Well, that's crazy because they behave very differently. But maybe, and this is the amazing leap of the human imagination and the hubris that in some sense is physics at the modern time. Maybe it's an accident of our existence. Maybe there's a background field throughout all of nature. And what happens is that the particles that convey the weak force interact with that field, and it's like, as I often say, swimming through molasses. As they interact with that background field, they experience resistance, and they begin to act like they're more massive. If you push your car, if your car runs out of gas and you push it on the road, you can get it going. But when it goes off the road and hits the mud, it stops. It feels heavier. So it's like there's this cosmic mud everywhere, and the particles that convey the weak force experience that mud, and the particles that convey electromagnetism don't. Well, that's beautiful. That's a nice story, like a biblical story. And if that were the story, if that were the way science were, it would just be like religion. But if there's that mud, quantum mechanics says if there's a field throughout space, if you slap that field hard enough at a single point, really hard at a single point, you'll kick out particles. That's what quantum mechanics tells us. So there's a prediction. So we just have to build a machine that slaps empty space hard enough at a single point, and will maybe produce the particles associated with that field. The field's called the Higgs field, and those particles. And so one of the purposes of the Large Hadron Collider was to discover those particles by slapping empty space hard enough. It's really a kind of a S&M machine. I was sure they wouldn't see them. It just seemed like such a slimy, simple explanation. It seemed too good to be true to me. And that's why I was so surprised that that explanation is actually true. These particles exist. Now, for me, to answer your question finally, after a little bit of physics, the idea that these fundamental scalar particles can exist changes for me the entire picture of trying to understand fundamental physics. And I've been thinking lately a lot about the implications that may have for the dark energy that governs the universe. It opens up for me a whole range of explanations before that I hadn't considered, because I just thought the Higgs explanation was just too simple. And nature always surprises us. And this, it just seemed crazy that we would guess the simplest answer and it worked out. And so I guess I was surprised, as I am by being surprised. So that's a short answer to your question. Yeah?
What do you think of Jason Lau, who says that we should be seeing a lot of stars being born and a lot of stars dying, a lot more than we are seeing today? And he says that's proof that the Big Bang is not true and all those things are wrong.
Well, I guess the evidence of the fact that I don't know who he is suggests that I don't think much of what he talks about, I guess. Maybe that's the only way I can put it, I guess. Okay. I mean, obviously he's had no impact. I don't want to seem, well, I guess I don't mind seeming pretentious. It's fine. But I know of people whose work has an impact on my work. And if that doesn't have an impact on my work and all of my colleagues, then I don't know about them. But look, the important thing but let me be a little less facetious. There are lots of mysteries and there are lots of puzzles. And so when we measure things, we often see things that don't agree with our ideas. But that's the hallmark of science at the forefront. When you're tentatively looking at things, often you see stuff that doesn't seem to fit. Most often, the anomalies are wrong. And in fact, we have to be, this is probably more important for this group, the easiest person to fool is yourself. And so we have to be on guard, not just about others, but we have to be skeptical of ourselves. That's probably the most important aspect of skepticism that I think I can convey. And that's particularly important for scientists. Because if you're measuring something and you find something strange, the most immediate response is, I've discovered something important. It's significant. And what you have to do as a scientist, again, as Feynman said, is you have to work equally hard to prove yourself wrong. That's right. You have to, most likely, you're making a mistake. And it's very, very difficult if you discovered something potentially wonderful, potentially earth-shattering, that something can make you famous, to have the courage, the intellectual courage, to say, it's probably wrong, let me figure out what I'm doing wrong. And so it's a really important process that experimental scientists, and to some extent theoretical scientists, but since I'm a theorist, we just talk, it's easier. Experimentalists actually do things. And to check your work and to try and prove yourself wrong. And then if you don't, your colleagues might. And so there are many times since I've been a scientist when, for example, I like to say, I was sure dark matter was real because it had died and been reborn so many times, and everything that's real has been reborn, as we know, has been. In any case, because there's so many times that you think some implication of your theory implies that there are too many stars, there are too much clustering, and then what you find is when you look at things more carefully, that's really not an implication. So people who claim that everything is wrong are generally wrong. And the reason is the Big Bang, that's the other thing. When I hear someone say, look, this doesn't agree, and therefore everything is wrong, that's just not the way science progresses. Science is based on a huge amount of experimental data, and the hallmark of progress is not to show everything's wrong. Einstein didn't show everything was wrong. In fact, Einstein did exactly the opposite. Einstein showed everything was right. What there was two theories, one of Maxwell, theory of electromagnetism, and one of Galileo, that when you're moving at a constant rate, you continue to move, and you can't really tell whether you're moving or not. All of you have had the experience of, if trains in Canada are smooth, of being in a train station and looking at the train next to you, and it was moving, and you didn't know whether you were moving or it was moving out of the station. Well, it turns out those two things are both right. They're both obviously true because they're both satisfied by the test of experiment, but they're incompatible. So what Einstein said is, I'm not going to throw out those things that are right. I'm going to show how those apparently incompatible things can be compatible, and it turned out the way to make them compatible was to show that time and space are relative, an amazingly brave thing. So I get hundreds of letters, I get tens of letters every week about it, with theories of the universe explaining how everything we know is wrong. And the minute someone says that, I know that I can, if I was like, I think, Lord Kelvin, who used to read, in the old days before they came in as emails, they used to be hard paper. And one of my favorite responses to those crackpot letters was his when he said, I'm sitting in the smallest room of my house. Your letter is currently in front of me. Soon it will be behind me. Okay, maybe one or two more, but we've got to go. One more, Jen.
I was in a room where Freeman Dyson took the side of religion in the science versus religion debate, and I wondered, is physics generally a safer haven for atheism than biology, for example?
Well, the key point to... Freeman just likes to be contrary. Freeman's a good friend, but he generally disagrees with whatever everyone else agrees with. It's just his property of him. And I think part of his... I read when he won the Templeton Prize, I thought, great, this is a chance for them to really be told off, because I respect Freeman greatly as an intellect. And I was very disappointed to see that he was so friendly. One of his kids is a minister, in fact. But the point is that the thing about science that people don't realize is that, as Steve Weinberg, who is an atheist, a Nobel Prize-winning physicist, has said, most scientists don't think enough about God to even know if they're atheists. God is just irrelevant. So it's not as if physics or biology are one or more safe than the other. God doesn't enter into it ever. In any scientific meeting, in any subject of science, God is irrelevant. And so it's the same everywhere. And maybe I think I have to go. I'm really sorry. I wish I could stay with you longer. Thank you very much.
Thank you so much.